So essentially, I hope all of you own. You can't see my screen, I guess. Yes. So yeah, give me a moment. Yes. Can all of you see my screen, guys? Mm, okay, lovely. Okay, so since we are discussing problems on linear algebra of past year ISI, so we have discussed our topics like this. I hope all of like this is our syllabus in linear algebra that we have covered, and we will be discussing past year problems now from ISI on linear algebra. Okay, so I will be just taking a question from 2021. Um, the first question of 2021 PSA, okay? 20219, I'm so sorry. Yeah. So this is the first question. Hello, guys. Yeah. So yeah. So this is the first question of 2021, 201. I'm so sorry, of ISI PSA. So let's see how we can do this problem together. So we recall all the knowledge that we have taught you in our previous classes. So yeah. So please be focused. So A is a matrix M cross N with all real non-zero entries. Let B be obtained by A by replacing A11 by 0 and keeping all other entries unchanged. Okay, think about this possibility. So um think about this. So let's take an example. Okay, and let's explore. Whenever we have this problem, let's explore. So it's like this. People are joining. So let's take a 2x2 matrix and let's see what really happens over here. So we have, say, A11, A12, A21, A22, and we are replacing this A11 by 0. Okay, and if we're replacing this A11 by 0, so it's happening that 0, A21, A12, and A22. Okay, so apparently it may happen that, okay, observe this very carefully. What is the rank? The rank, you can dimension of the, or rather the span. So essentially, what is the rank of a matrix, how we can define it. So essentially it's the corresponding like suppose consider the columns over here. Okay, and essentially if you take this column and take the span of these columns, which is called the column space, then the dimension of that column, which is a vector space, is called the rank. Okay, so also you can indirectly you can tell it that rank is the number of linearly independent columns, independent, that are the basis of this span. Okay, columns. So do you all agree with this, guys? Any doubts in this aspect? So we will be explaining in much more details because people may not know stuff over here. So essentially we have a set of columns. We have taught this in our classes, but yeah, for all the people over here, so there are n columns there. So the basis of the column space, that is the span of the columns, is actually what is the dimension of the whole matrix, the rank of the whole matrix rather. And the rank of the whole matrix is therefore formed by those linear combinations of the linearly independent columns, right? And that is what is the basis of the column spaces, the number of linearly independent columns. So how do you find that? So but the question is that here all the columns are remaining same except one, the first column. Okay, so what is really happening is that all the columns are remaining same over here. So let's see what is really happening. First column, second column, third column. Let's say n columns are there. It's m cross n. So how many columns? N columns must be there. Yep. So everything is remaining same. Only the first one, this is becoming 0. Okay. So let's say for A, this has R. Okay. So I'm just making you write the whole thing because in your ISI exam you have to write the proofs. Okay. It's really important. So you have to write the proof. So essentially this is 0. And what is really happening over here? So in the B matrix, I'm so sorry. So here, let's say R like this. R is a rank say, so the R columns are linearly independent, or Li, which I say. And what is happening is that you're changing this to the matrix where it's 0, only this is changing, and rest of the things are remaining same. Okay, so what can happen because of this 0? What can happen because of the 0? So the idea is that this can be made, so you can assume that this is one of those linearly independent columns. That is the basic idea. You can assume that this is one of those linearly independent columns always. So that is the main idea over here. Always you can assume the first is a linearly independent column. So, and rest of the r minus 1 are already there. Okay, this is the 1 and this is the r minus 1. So when 0 is introduced, what can happen? This can become the dependent on those r minus 1 vectors. Okay, so the rank may reduce by 1 because of this change in 0, or the rank may not be changing. Still then it's linearly independent. So this is the basic idea. So first you assume that the first column is one of the linearly independent columns, and the rest of the r minus 1 is over there on the right hand side. And if you just change it to 0, the change can happen. It can become linearly independent or not. So essentially the rank is turning out to be r minus 1 or r depending upon this change. Okay, any doubts from you guys? I hope all of you understood it. Tishika, any doubts? Hema?
Understood.
Okay, very good. So yeah, I hope all of those don't have any doubts too. If you have any doubts, please let us know. Okay. So yeah, so this is a basic idea. So we have dealt with column space. We have dealt with how what is exactly the rank in terms of the column space, in terms of the corresponding linear independence of the columns, and how we can sort of use it to compute this. Okay. So that's the basic idea. It can increase also. So yeah, so it can increase also. So tell me, Devar, how it can increase. I was just looking for this answer. Tell me how it can increase. Give me an example. So this is the basic idea. What Devarga has told. You should have pointed it out. Is that if whatever something was there, it may have been linearly dependent at that time. But Devargo, tell me one thing. I have already assumed this is one of the linearly independent subsets, linearly independent vectors. So what can happen? So can you give an example to justify? Can you justify this? Can you justify this? Okay, lovely. So this is what Devargo is telling. 1 0 0 1, I guess. Okay, this is already and 0 0 0 1. Yes. Session. No, wait. What is happening over here? So it's reducing, right? Hemant is telling 1 2 2 4. Yeah. Yes. So this is what exactly I was looking for. So here, observe this very carefully. So there was a small glitch over here. You have to understand that. So if it was 0 over here, guys, if it was just a minute, someone is trying to join. So what is really happening over here is that if this is 0 over here, so I'm trying to convey this. So if this is suppose 1 over here, so this is one of the linearly independent columns. Okay, there is 0 over here. If you change it to be this, then what is happening? This two are become linearly independent, right? So essentially the number of linearly independent vectors are increasing. So what can happen is that if you change it to 0, what can happen? It can decrease like this. For example, let's say 1 0 0 1 is there. Okay, let me give examples. So how it can decrease, increase, and remain same. So for 1 0 0 1, I will give an individual example. See, this is a really important step. Okay, in exam you can really do it in an instant, but exploring that aspect and doing the problems is really important. So that's why it's like what we really love to do. So essentially, let's say from R it's becoming R minus 1. Let's take that example. How from R it can become R minus 1. So for 2, how it, let's say R equal 2, we are doing it for 2, say. For 2, how it can become 1. So from 2, this is how it can become 1. What the Vargas told. From this, it's coming out to be 0, 0, 1 0 1. So yeah, so this is one vector, this is not a vector actually, so therefore its rank is 1, its rank is 2. You see, yeah, same as this. You can also do it as, just give me a moment. So you can also do it like this. So let's take another example. Let's take this example. Let's take the linearly dependent, and you make a change. Now it's becoming from 1 to 2. See, so that's the idea. So 2 to becoming 1, 1 to 2, and it can also remain same if you just take a random stuff like a 1 3, 1 4. If you just take it and change it, it's 2 already here. It will become 0 3 1 4, which is becoming 2. So it can go from R to both R plus 1 minus 1, R plus 1, and R remain R. Okay. So why? Because even if you assume the first one is linearly independent, okay, among the linearly independent, if you introduce this 0, that this vector can become linearly independent again. These are vectors. Okay, this vector was linearly, so suppose this vector, if you take this vector, there are only R minus 1 linearly independent vectors over here. Okay, if you include this vector, it can become R over on the right hand side. Okay, it can increase by 1. Okay, that's the idea. So, and similarly it can decrease by 1. So essentially this is the idea. Okay, so I hope all of you understood this. Any doubts from your end, guys? Any doubts from your end? So yeah, so this is really important. You should understand this, how it can really happen.
What was the example for increasing the rank?
Yeah, increasing rank, yes, as I told that for increasing rank you have to first check a linearly dependent stuff like this 1 1 1 2 1 2, and even if you include a 0, it becomes linearly independent. See, Tishika, you see, two vectors are linearly dependent. It's like this, two vectors are linearly dependent like this in the matrix, and if you just change it by 0, it's like this, two vectors are linearly independent, say, or let's say three vectors. Consider these three vectors. Three vectors are linearly dependent, that is, they are lying on a plane. Let's say they are lying on a plane like this. And if you just change it, one of them to be 0, it is just moving up once. So they are becoming linearly independent. See, that's how rank is changing. Let's see how the rank is remaining same. So these three vectors are linearly independent like this. And if you just change it once like this, just one value, it is still linearly independent. So rank is remaining same. And rank is increasing, I told. Now let's say decreasing. So let's say three vectors are like this, and you just change it to 1, they come out to be on the same plane. So they're linearly dependent again. So this is the idea. Okay. I hope you understood, all of you, how it's happening. Tishika, Nisha.
Yes, sir.
Very good. Okay. So let's move to the next problem. From the people who are not our regular students, I hope you're understanding, guys. Pratiksha, Devajyoti, Anurag, Jishan, Akriti, Vendrila, Rahul,
Yes,
Shaumadev. Okay, Shantanu. Lovely. Great. Let's move to the next problem. Next problem. Let me find it out. Okay, this is really easy, I guess. This is very mainstream. This comes also IIT Jam, all that stuff. I mean, linear algebra of IIT Jam and ISI is same type. Okay, so you can really. Yep. So this is, let's say T is a real number. I'm sure people can do this here. Most of the people. So T is a real number over here. The rank of 0. Okay, by the way, before I continue to this next question, there's a research problem for you. Okay, mathematical question. So the thing is that instead of this changing, so essentially you see 0 has no value over here. Okay, it can be replaced by any real number. You see, it can be replaced by any real number. Okay, let's say k. then it will be remaining same. So essentially, it just matters whether you are changing it or not. So my question is to you that for an n cross n matrix, okay, the maximum, let's say for a rank is n, okay. So my question is that how many changes do you need to change the rank of the matrix? Like suppose you're making k changes, or let's say alpha changes. So how what is the possibility of the rank? Is it r minus alpha to r plus alpha? If if it's in the same, so you can prove it. Think about this research problem, but I will give you a hint that alpha depends upon, see, if you just make two changes in the same column now, it is not really happening much, it's not really giving much, right? Because two changes in the same column is equivalent to one change in the one column, right? Because it's linear independence of the column. So you can prove that if all the alphas are in the different columns, then the rank can change from r minus alpha to r plus alpha, or rather it's a conjecture, is it true or not? Okay, you should play around with numbers and think about this, okay, whether it's true or not. Okay, okay, so that's it. So let's move on to the next question. I hope all of you understood this question. So I'll just suggest you guys, so more than the examination purpose, you should always explore with this kind of ideas, okay? It makes your best much more stronger. When you're given a question, never stop there, just explore the question. Just like suppose you're going on an adventure and you're exploring the place, just explore the problem, like what if I make this small change, what will be the case, and you will feel good because you will make your own questions, you will solve your own questions. So that will also enhance your problem solving skills, okay, which is much more important than giving your exam, like whatever, passing in your exam, or yeah. Okay, so let's move ahead in this, like in the to this problem. So t and real number, and the rank of the matrix 0 2 2 1 t 2 t minus 1 0 is equal to what? So yeah, how can you find the rank of this matrix? Any ideas? What is the quickest way? So these are algorithmic problems, right? So what is the quickest way? What do you think? Any ideas? I would really love to interact with one of the people who are not a student. Yeah, yeah, Rahul. Yeah. So tell me. Ha.
Echelon form.
Okay, you want to do in row echelon form? Okay. Okay.
Determinant will for the equation.
Okay. Who is this, by the way? Shantanu Naik. Yeah. Okay. So yeah. So one idea is determinant. Let's see. Let's collect the ideas. Okay, of people. One idea is determinant. Another is row echelon form. See, I will tell you why determinant may or may not work. So determinant only gives the idea that if its rank is equal to 0 or not. You see, determinant is equal to 0 if and only if, like, it's not full column rank. Right, Shantanu?
Yes, sir. One hote pare.
No, please talk in English because people are over here who don't understand Bengali.
Sir, maybe there may be rank one. We may skip that case. That's why determinant may not work in that.
Exactly.
But we can check by putting the value of t after row reduction, it will be easier.
Yeah, it can be easier one. You're right. It can be an easier one. So perfect. So determinant may not work over here if the determinant, if you have got an option, right? It was 0 or 3. So 3 is over here, okay? So you can easily check whether it happens or not. But I am sure it will not happen. So can someone find the determinant? I'm just exploring, okay? This is probably in a exam hall. I'm just exploring for your own sake. So can someone find the polynomial determinant? I would really like if someone find it. I think the determinant is a quadratic.
T square minus 2t plus 2.
T square minus 2t plus 2. Is it? Pratiksha? Okay, thank you, Pratiksha. Okay. Oh, plus 2. Yeah, so I think this has a, I think this is solvable, right? Or is it? No, wait. Does it a real solution, guys? इसका determinant क्या है? 4 minus, oh, oops, lovely. So determinant, so there exists no t such that determinant is 0. So therefore, is it full column rank? What do you think? Huh? Yeah, it's a full column rank, right? So see, I didn't know the solution though, but it's just, so essentially these are ideas you must have in your mind, small ideas. It's like with problem solving aspect. But yeah, so you must, if you have zero, if you didn't have 3 over here, na, I wouldn't have tried determinant. I just tried with the like leap of faith that okay, since 3 over here, let's try and see it. Okay, what really happens? So essentially t square minus t2t plus, okay, so this has no real solution. So therefore determinant is never 0. So therefore it's 3 for all t. But what we will do in the other aspect, okay? We'll do in different forms, another form. So that if suppose this option was not there and suppose some other question was there, so how would you have done it? Okay. So yeah, so Rahul or someone else who told Rohit in form, can you explain your method to your friends over here? Or anyone who wants to volunteer?
May I try?
Sure, of course. But
By operations, reduce it to the row radius echelon.
okay, please tell the algorithm. Suppose you're solving the problem in exam hall.
Okay, so make the last row in the first row first, then divide it by 2.
Wait, I didn't get you. फिर से बोलो.
Last row
Uh-huh.
changing to first row.
Last row changing to first row.
Yeah, R3 changing to R1, then divide R1 by 2, then 1 will come.
No.
Then make it.
No, what does it mean by R3 changing to R1?
Like I'm changing the row 3 with row 1.
Okay, how does it help in?
Making an operation.
Okay, so you're doing like this. Huh?
Then row 1 divides by 2. I'm basically reducing into the 1 0 0.
Okay, I see. Okay. So R3 changes with R3. Okay, and then you row 1 divides by 2. Okay,
Yeah,
R1
then
by
1
2.
will
So
come.
you get 1 1 0 2 minus 1 0 1 t. Okay, makes 1 second. Someone is trying to join, maybe, or is it? Oh no. Okay, fine. So okay, now what's you're trying to do?
Then R2 changes to R2 minus twice R1. So an
Okay.
operation R2 minus twice R1.
R2 minus twice R1. Okay, so okay, makes sense. So 1 1 0 0 t minus 2 minus 1. Okay, let me know if I am doing some mistake. Okay, guys. Okay, yeah, go ahead, Rahul. See, I've got this 1 0 0. Then you will be doing this 1 0, this one, right?
Yeah.
Yeah. Tell me, how will you do it now?
I need to make the third row 1 0.
You need to make the third row 1 0 1. You mean?
Yeah, below diagonal all will be 0.
Yeah, so you can easily do it. Oh yeah, okay, I see the problem over here.
Yeah, there's a problem.
There is no problem in such, but yeah, I mean, okay. So do you know why this is a row reduced form is why it works to understand the rank? Okay, someone is telling something that R2 minus. Okay, so you can do that, I guess. What do you think?
If we compare the last two rows, then we can say that from 1 we get t equal to 1 and t equal to minus 1. We conclude that the
Wait, tell again.
if the rank is not 3, then the last two rows must be scalar multiple of one another. If the rank is not 3 in this case,
Mm-hmm.
then if we take the ratio if t minus 2, if t equal to minus 1, then t minus 2 must be equal to 1. then it would be a scalar ratio. But we can see that from here, from the t equal to -1, and from here t equal to 1, from which we can conclude that there is no solution for such t that rank will be less than 3.
Yeah, you're right. You're right. I have another small idea maybe, which is that if we just reduce R1 minus R3, you're right. So why I'm doing, I will tell you. It becomes 1 0 0 0 t minus 2 1 minus t minus 1 t. Okay, why I did it? Because I'm trying to make you understand. Okay, I think it's not helping though. Just give me a moment. Okay, so this is actually easy from here in this case. The given thing that over here. So essentially, you observe that um, if so, try to understand. You're right. You're right. So essentially, what they told that try to understand. Let's assume that it's actually it's not possible, and therefore it's not 3. Say rank is not 3. So what he's telling that there is a scalar multiple which will really let it happen. So plus beta times 1 t minus 2 1 plus.
Okay, so now next what you can do is you can change R3 minus R2 by t minus 2. Then you will get in the third column last element, third row last element, you will get a t expression. Then you can prove that no
Okay,
real value is
okay.
existing.
Okay,
Then
that's a
it
good
will
thing.
automatically
So R3 minus R by R2 by t minus 2.
t minus 2.
So we get 1 0 0 1 0 over here. So t minus 2 ऐसे ही रहेगा. And we have 0 over here, right? And we have t plus, yeah.
1 by t minus 2. Now,
Sorry for my bad handwriting though, but yeah.
So if it will be 0 in any case, then this t plus 1 by t minus 2 should be 0.
Wait.
Right.
Which one is 0? Okay, okay. Yeah.
T plus 1 minus 2 should t plus 1 by t minus 2 should be 0 for the rank to be less than 3.
Yes. Right? Lovely.
So if you are getting a complex number, then it's not possible, right? As per the question, I think if they have asked a real value.
Exactly. So you understood what he really did. Essentially, he did the same thing, and he did more in a much more elegant format. So essentially, what he tried to, let's try to understand the algorithm. What he tried to do, Rahul. Nice one, Rahul. So essentially, he tried to like make this one 1. He tried to make the others 0. Okay. Why it is he's trying to do that? Because once he tried to make the others to 0, okay, and he can actually prove that this one must be 0. Okay. And that's the idea. So essentially you must rather prove that, like, also you can, instead of this 2, you can also do it like, I mean, I also don't think this is important. Okay, only 2 consecutive element 0 is important. Okay, or 2 row ka element or 2 column ka element. If you could do that, essentially you can prove that the other one is 0, which is in terms of a variable. So you can do that. Yes, you're right. And essentially in this case, if it's a very hard problem, what you can do is that you can essentially play around with this t and make the actual format, okay, which is a little hard, but yeah, so you can really do that. But first step, like if you want to play around with that, you need to do the determinant then. So yeah, okay, thank you so much, Rahul, for your response. And I forgot his name. Debojyoti, I guess. No, not Debojyoti. Who told? Shantanu. Yeah. Okay.
Sir, what were the options?
Okay, what options? Oh, options was 3 for all t. Okay. Okay, let's move ahead to the next problem. This is the interesting one, but I think it's actually okay. This is something interesting.
I think it shouldn't be actually option D. Yeah, they're correct. It's not D actually. because
Oh.
it's coming to equals to 1, right?
Wait, let me. I think I have done some mistake. Just give me a moment.
It's B. The option is B.
Okay, let me check. So what mistake did we have done over here? If it's t is equal to 3, then we have done some mistake now. So what mistake did we do over here? Did I compute determinant wrong? T square minus 2t plus 1 aa raha hai na? I mean, did you tell me wrong? I think some
No, it's correct only.
determinant is correct. Then what is the problem, guys?
When you got the expression right, if it's coming t equals to 1. For t equals to 1, it's becoming 0. So then the rank will become 2 if t equals to 1. Because it's coming t minus 1 whole square equals to 0. In the
But
final expression.
determinant ka?
Determinant plus 1.
Okay, you gave 2, right? There will be 1 actually.
Yeah, this was 1. Okay. Then of course, yeah. Yes, so essentially the first step, I think, yeah, this is a good step. The first step should always compute a determinant and see for which values it's actually. Oh, this I think it's a very good thing. Okay, no. See, the algorithm is very easy, not in row by echelon form. You should do in this format. First compute determinant to be 0, and you get the values for t for which determinant is 0. Okay, and you put on those values and see whether they're independent or not. What is the rank? You put the values of t and see whether they're independent or what is the rank. Okay, that is a much better algorithm rather than doing in row echelon form. Okay, so t is coming out to be 1. For t is equal to 1, it's 0. Yeah, sorry, because I didn't observe this calculation, I'm sorry for that. So 0 0 2 2 1 1 2 1 minus 1 0. So is it linearly independent? Of course this is not 2, because t is equal to 1 ke liye it is, but I think this is actually, if this is, so rank cannot be 1, okay, because it's not multiple of 0 2 2 all of them, so rank must be 2. Yeah, this one, right? Is the answer B?
Yeah, it's correct. B.
Yeah, so we don't need row echelon form, but yeah, we learned something new, right? Thanks for that, Rahul. We learned something new, how to do it with row echelon form. We of course need it somewhere else. Okay, let's do this next problem. This is an interesting problem. Just give me a moment. No, I think I did some mistake. Where are the other problems? Okay, 2019 ka, I guess all the problems of linear algebra is complete. Let's go to 2022. 2020. 2020 ka. Okay, yeah, this problem. Oh, I have been taking this problem for. Yes, someone is coming, but I am not being able to admit them. You know why? How to see which people are coming and going? Anyways. Okay, so there's a problem. All of you can see the problem. This problem is really interesting in the aspect that yeah, this formula of differentiation. But yeah, so it matters like how you really do it. Okay, so which way you should do it. So many people don't know this, but like there are a lot of juniors over here, guys, of yours. Okay, so we should help them. How do you think we can approach this problem? How do you explain it to your juniors, guys? So just use the formula of differentiation. But why do you think so? Like what is the, will you compute the determinant first? This is a determinant, right? So I hope this is a determinant, right? This is what I mean by determinant, right, guys?
Yeah.
Yeah. So so now how will you do it? How are you planning to do it? Tell me. How do you really do it?
Differentiate one rows or columns and then remaining rest plus add.
Wait, I didn't get you. Can you repeat again?
Like differentiating the row, first row, then plus remain same, then differentiating the second, then adding it.
Okay, why is this result true?
This is a result time like this.
No, I mean you should no. This is not the way. Okay. So,
Sir, may I try?
sure. You must try.
Shantanu ma'am. Sir,
हाँ.
e to the power x টাকে যদি sin x plus I cos x এ split করি,
That's really good. Yeah, actually that was what I thinking of. Yeah, go ahead.
sir দিয়ে এটাকে sum of two
Please talk in
determinant এ
English.
নিতে পারি। Sir, then I can taking the মানে considering the first column, I can split the determinant into sum of two determinants.
Okay.
Like so then I think I think fx will come 0 directly over there. I'm not sure because sin x, sin 2x,
No, wait.
sin 3x,
Okay. You're trying to find out effects.
yes, direct fx will be if there's maybe.
So I don't know who the person who told the other result. Like who was that? Who some like previous person? Who was that?
I said it.
Yeah. So Rahul, I don't know like how did the result come. Can you tell me the result? I don't even know that result.
So it's like as far as I can recall, it's first differentiate the first row, okay, and
Okay.
remaining will be same. Remaining two rows remain same. Then differentiate the second row, and the upper two remain same, and then just add this. So how you differentiate a determinant? It's the result
Oh.
for differentiating a determinant. I
Okay.
learned this in class actually. Yeah.
Okay. No, मैं मुझको तो इतना formula याद नहीं रहता है. So for guys like me, I
Simple
don't.
approach, that's it.
No, man. I cannot accept this, man. I have never learned any one formula in my life, so I cannot remember this. And if I think I don't think ISI gives problems just based on formulas. Okay, I think there are some better ways. I think what Shantanu was telling. Yeah.
One more approach can be, to see the trigonometry formula if I can.
Yeah. I think that's a better way to approach, guys. So let's try to understand that. I don't know, like, let's try to try that. But personally, I feel there are a lot of good forms over here, like there's a very symmetric form over here. I can easily observe because I mean, I am trying to find the determinant in terms of these rows, okay? So if it's like e to the power 3x times sine 2x into cos 2x, I don't know, like
We can try to make it 100 also, like in that format. Then it will be simpler.
100
We can reduce the function basically,
2.
like do a operation wise, row 2 changing to minus 2 r1, and we do that. Row 2 changing to minus r square basically, minus r1 square.
Is R1 square allowed? I don't think so. I think it's linear combinations. You understand? And R1 square karna is not a row echelon form. Multiplying two rows is a row.
Scalar we cannot. It won't be scalar multiple.
Yeah, it's because it's on a linear operation, That's why.
Yeah.
Okay. So okay, but what I think is that since I see the pattern, I mean, if you just see the corresponding thing, sin x into cos 3x minus sin 3x into cos, that is, I don't know. I think that is sin 2x. I'm not sure about that. What was sin a minus b formula, guys? I forgot. Sin a cos b.
Sin a cos b minus cos a sin.
What is this? Sin a minus b, right?
Yeah.
Okay. So I think I can see that easily because of the determinant stuff. So do you remember like how to do the determinant of the row form like this? It's e to the power 3x times. So let's e to the power x. Let's say e to the power x times sine 2x into cos
Sin
3x.
2x cos 3x minus cos 2x sin 3x.
So essentially, it's turning out to be minus sine x.
Then some sin formula
Minus
will be
sine 2x times क्या आता है sin 3x cos Sin x into cos 3x. Am I doing it correctly, guys? Sin x cos 3x. Am I doing correctly? So I'm doing like e to the power x into this minus this. I'm taking this times it this. Oh, okay, so minus e to the power 2x into sin x into cos 3x minus sin 3x into cos x. That is minus sin 2x. Okay, lovely. And plus e to the power 3x into sin x into cos 2x. Okay, that is minus sin x again. Okay, that makes a lot of sense. So, okay, yeah, I think then it's easy. I mean, there was kuch nahi in this problem. Yeah, I think then it's easy.
Just enroll you.
Yeah. I think it's easy now. Yep. I think it's really easy now. Is the answer 0? Any one person have done it? 0. Someone has done it.
Yes, sir.
Okay.
Using complex number, I think it would be a directly we can say.
We can write ex in the form of complex number.
Okay.
Pretty.
Once would be directly.
Okay, let's see it. Let's say it since people are. So you are writing e to the power minus ix. Sorry, e to the power x. E to the power x is what? Can you tell me? Because it's e to the power ix is equal to.
Sin x plus iota cos x.
Yeah. Well, who is this by the way?
Tishika.
Tishika. Okay. Sin x plus I cos x. But here there is no iota. So it's in terms of ix.
The direct sin x plus cos x will do. From the Taylor series, we can see it.
No, wait. E to the power x is equal to sin x plus cos x.
Sir, 1 minute.
Don't make this gross mistakes.
What they are doing is cis theta basically. What you have e to the power ix equals sin x plus I cos x.
Yeah. So essentially it's e to the power ix here, not ix. Okay.
I cos x, yeah.
So it will be I cos x. So now, do you know what is cos of a complex number? I once remember. So I made a prodigy child. Okay, I was in my I think first year. So he was from my school. So he was in class 7, and of course he was proud of his mathematics. He already has a paper by that time. Okay, mathematics paper. So he came to me and told me, let's talk about mathematics. I'm okay, sure. And then he came to me and told, tell me what is sign of a complex number. Oh no, he asked me, can sign of something be greater than 2, greater than 1? I knew it, so I could have told him that, but I didn't expect that from a class 7 guy to ask me that, okay? So just for your understanding, sign of a complex number does exist and it can be greater than 1. So it's your exercise to find out how it can be, okay? So think about that. And it's not easy. So that's why this method will not work. That's why I avoided that. Okay, guys? So yeah, just a short story that suddenly came to my mind. Okay. Okay, I think it's pretty easy now. Any Tishika, I hope you understood where we are going wrong. Yeah, log of complex numbers also exist. Yeah. Devargo is from mathematics background. Of course, he knows. Okay, guys. So let's move to the next problem. Hmm. 2020. आ गया. Not really too much problem comes from complex numbers. So next day, by the way, for those people who are doing classes with us, we will be starting real analysis revision, okay? And we'll be moving on to the for 3 days real analysis revision, and then we're doing the problems of last year. As I've seen, IIT JAM and ISI MStat both has more about real analysis, probability, and statistics. Okay, coming back to this problem, mostly real analysis and probability. Okay, let x be this 1 by 2 this and a be this, and x transpose. Okay, if b is equal to x a x transpose, and then x transpose b to the power 1 to 105 is what? Yeah, tell me. This makes sense.
X is a orthogonal matrix.
Ah, lovely. Yes. So you must observe this x of.
X transpose and X inverse will be same. Then B and A will be similar matrix. Since B equals to X.
So can someone tell me what does this matrix, what is the geometry of this matrix, except Devargo? Because he has a math background. So except Devargo, can someone tell me what is the geometry of this matrix? So it's a matrix.
Draw the row picture and column picture like that.
Okay. So just give me a moment. So remember that I sort of I gave in the group 1 linear transformation ka thing na. Just give me a moment. I will just open that and I will show you the picture. Linear transformation ka picture. It's really beautiful, you know. I was teaching linear transformation that day and I just showed these people out there. It's really beautiful. I will again show it to you. I will just stop presenting. So can you see? Just give me a moment. Can you see the picture, guys? I will just do it for the streaming too. Can you see the picture? You see a Mona Lisa over there? All of you? Hello? Yes. So I will just show you. Can someone repeat the first? Can someone tell me like what was the first one? First one kya tha? First row ka? First element kya tha? Can someone tell me?
Root 3.
Root 3. Okay, root 3.
1.
Okay, I think
The half is outside. It will be root 3 by 2.
root 3 by 2. I think I think
One
square
half
root
is out.
3 by 2. Okay, the B was B kya hai? This is the B.
1 by 2.
1 by 2. Okay.
Minus 1 by 2.
You see the changing of Mona Lisa? Observe this very carefully. C is minus 1 by 2.
Yes, sir.
And this one?
Root 3 by 2.
Root 3 by 2?
Yes.
Is it root 3 by 2? That is. Oops. Oh, just give me a moment. Okay, lovely. You see? What kind of rotation is this? What kind of linear transformation is this? Mona Lisa. Hi. Okay, so this is what is a linear transformation all about. There's no animation to be such. So what do you think is a linear transformation all about? Is it 90-degree transformation? It's a rotation, does it seem like so? Does it seem like Mona Lisa is rotated? What do you think? Is it a rotation? By the way, how will you understand, given a picture, tell me, how will you understand whether a picture is rotated, like picture size is same or not? Tell me. This is a very important question. So how will you understand that suppose you have this Mona Lisa picture, okay, and I apply a linear transformation on that picture and you get another picture. Okay, these are all the reason, this essentially every mathematics behind, if you are reading computer graphics, you must be knowing this, okay? So this is essentially behind computer graphics, okay? We see all the animations out there in the world, all the 3D projections and stuff like that. Essentially, it's all about this, okay? That's why it's a very important question if like for your job also. So there's a Mona Lisa picture and applying a linear transformation on that. So how will you understand the picture size is same or not? How will you understand that? Did all of you get my question, guys?
If the starting point is same, like origin over.
Origin will always be the same because it's a linear transformation. So what exactly is happening over here? Each Mona Lisa point is going to another Mona Lisa point, okay? So yeah, tell me, how will you do it? It's really easy. So the first question when I see is over here, okay, it seems like a rotation, but the question that came to my mind is that is the picture size same? What do you mean by size over here? What do you mean by size? Can someone mathematically express that? What do I mean by size?
The determinant of the matrix.
Lovely. Yes, exactly. So as I told last day in my classes, that exactly right area, Pratyusha. So as I told in my last class, that we understand that whether something, so essentially determinant is essentially equivalent to the area. Okay, I was asking in some sense that whether the area is same or not. That's what I am meaning. Okay, that's what I'm meaning by whether the size is same or not. And let's compare the determinant of this. Let's compare the determinant of this. What is the determinant of this? It's can compare the determinant of this, guys. It's root 3 into root 3 plus 2 1. That is 3 plus 1. Okay. Okay, it's root 3 by 2. Sorry, it's root 3 by 2 by root 3 by 2. That is 3 by 4 plus 1 by 4. That is 1. Okay. So therefore the determinant is 1. So therefore the area is changing. The area is remaining same. So the determinant is equivalent to the area of the area of the picture. Okay, in some sense. So why is it so? Because the determinant is same as I have last class. Its determinant is same as the determinant of the area of the parallelogram formed by these two column vectors. Okay. So essentially, linear transformation is uniquely defined by how these two column vectors are changing. So essentially, their area is changing. So they are not changing in fact. So you can prove that. So therefore, Mona Lisa, okay, area is not changing. Okay. Suppose Mona Lisa area is not changing, then it seems like a rotation to me. Okay. We can prove it like what's the rotation matrix now. Okay, any doubts in this format, guys? I hope all of you understood this. What I try to tell you. So this was not the way I was taught in my college. No, maybe I was taught in my college, but not you are taught in your college. I guess so. So it's really important to understand this. Okay, that's why I spend a lot of time to understand the like. Also, there is a linear algebra is also used. Like if you ask me the question, general question, that where is linear algebra used? So this is suppose you're giving a job interview. Okay, people will ask you, say, what is the linear algebra used in statistics? So why you are studying linear algebra for your statistics? Why do you need it even? So there is something called principal component analysis if you learn machine learning and advanced statistics, where you use the ideas that okay, this is so where you transform the data space. Okay, the data space is actually a vector space. So you want to make information, extract information out of the data. Okay, so you transform the data space in such a way that you want to form a line where the maximum information of the variability of the data lies, and that's what principal component analysis is all about. Yeah, linear algebra is also used in multivariate distributions here, right? But I'm telling in terms of statistics and data analysis. Okay, even if you're learning machine learning, it's important that why principal component analysis, like whatever, why linear algebra is coming up, because linear algebra, the matrix is used to present the data. Okay, and you know that, like, of course you know that projection of something. So essentially you know that I hope you know about that linear regression actually the projection on the subspace, column space of the whole data space, right? So essentially what is happening, I'm just deviating, okay, because I don't like to discuss so many problems like just for the exam. I want to give you some different perspective towards these things too. So
that is why the coefficient is between -1 and 1.
yeah, so I will just show you. Can you see my screen, guys? Normal writing screen? Huh?
Yeah.
Okay. So essentially what is happening in case of regression, so you are essentially doing y is equal to x beta plus epsilon. So what essentially is this? So you have this data, okay, x. So what you're forming is that you're forming a data space like this. This is a column space of the data. Okay, this is x beta actually. All the x space of x beta is all possible x betas in your life, because the beta is a variable. Now what you're essentially trying to find, you're trying to find a beta hat, right? For this, such that it is this is like such that you're approximating y is equal to x beta hat. That means what? You're trying to find a point. This is a y, say, okay, this is a y vector. You're trying to find a point, a beta hat, that is a point, a line, a vector on this line, on this plane. The x beta is set of all x betas, right? So you're among those betas, you're trying to find a beta hat, and essentially a x beta hat, that is a vector in this plane, says that this is closest to y. Okay, how this is closest is turning out to be, this is by the loss function. The loss function is the least square method, the OLS, the ordinary least square you're doing. So since it's quadratic, it's coming out that the distance is quadratic, it's coming out that okay, this is the perpendicular distance must be minimized. If you have taken some other loss function like least absolute deviation method of linear regression, or maybe something else, it would have been something else. Okay, so but here to make yourself much more, you take the Euclidean distance. Okay, and for the Euclidean distance, it's minimized. The distance is minimized when this is perpendicular. So essentially, this is a data space, and you have this y over here, which is outside the data space. That's why the error is here now. The error is a vector. So essentially, you're trying to find the x beta hat, and this error over here, this is x beta hat, such that you get the y hat. This is the idea. X beta hat and error hat, this you get a y. And we have taught our students like using these ideas only. Okay, and all the I was just transitioning towards linear regression. All the relationship, like covariance of this, where am I? Y hat minus e hat, y hat minus e hat is what? X beta hat is perpendicular to e hat, right? Y minus e hat is perpendicular to e hat. So it makes sense from the data, right? Perpendicularity is happening. So we can using you assume all this and you can do all these problems. Okay, so linear regression is nothing but a projection. So that's why it makes sense. Okay, this is the beauty of this. If someone asks you in the interview even like what is the use of linear algebra, why you are studying linear algebra, this is how you should know. This is how you should perceive the whole subject, not like just formulas and stuff like that. Okay, and also you will learn about linear algebra and how statistics is related in higher like when you do your masters too. Okay, so that's it. Yeah, I will not do further stuff. That's it for today. So I hope you learn. Okay, I didn't complete this problem. Okay, let me complete this problem. I deviated too much. So essentially, you can find out that how a rotation matrix looks like. And this is X actually, and this is A. Okay, so how will you do this problem? And so after discussing all this beautiful stuff, I'm not in the mood to solve this problem. So someone help me with your ideas. Give me your ideas. So how do you approach this problem? So B, okay, so someone told me, oh, it came out that X is an orthogonal matrix. Yeah, rotation matrix is an orthogonal matrix, okay? So X into X transpose is equal to 1. So therefore X transpose equal to X inverse. And therefore you can easily find out X transpose over here. So therefore you know that X inverse is equal to 1 by root 2, root 3 minus 1, 1, root 3. Okay, this is X inverse. So B is over here. It's equal to AX transpose. And suppose you want to X transpose BX. So you get what? X transpose multiply, you get this, and you get A. And okay, you have B to the power 105 over here. Okay, I will just do the calculation now. It's becoming a bit. So B is equal to XA, XA, X transpose. So observe this, that B square is what? B square is X, A, X transpose, X, A, X transpose. So this X transpose becomes 1. So you get that X, A square X transpose. And if you do induction, then you will get B to the power N is equal to X, A to the power N, X transpose. And since it's the inverse of it, you multiply X transpose B to the power N, A, X, you get A to the power N. Okay. So therefore its main observation is that this is an orthogonal matrix. Okay, that's why I just turned into rotation matrix, and you got that. Therefore you just compute A to the power 105 now. How do you compute A to the power 105? A to the power 105.
B equals to XA X inverse, then actually A and B become similar matrices.
Yeah, can you tell me once again?
If B equals to XA X transpose, since it's an orthogonal, then X transpose will be X inverse. So B equals to XA X inverse means that B and A are similar matrices.
Yeah. So
Then their eigenvalues and everything will be same. No?
Okay, so
So computing a to the power 105, b to the power 105 is same as computing a to the power 105.
that's what you prove over here.
Yeah, same thing. we prove.
But how do you compute a to the power 105? But you're right, of course. How do you
b to the
compute?
power 105 is required. So it's basically nothing but a to the power 105. That's what I'm saying.
No, it's not a to the no. I mean, essentially you need to compute a to the power 105. Okay. How do you
Yeah,
find that?
that will give the answer.
But here you observe that none of the option is here. It's not required to compute. So there must be some value in this. So essentially you just compute a square first. Okay. Just compute a square and see what is really happening.
In square is coming up to the identity matrix.
A square identity আসছে? Oh, lovely. It's idempotent matrix it is. So just multiply this. So that's the idea. You multiply this 1, 1, so you get 2, 1. Lovely. So 1 minus 2 plus 2, 0. Lovely. Oh, nice. Yes, it's coming out to be. Oh, is it coming out to be? Yes.
Then the answer will be A, I think.
Yes. The answer will be A. Simple. Okay. Easy stuff. Okay, so it was really nice talking to you guys, and good night, all of you. And yep, so all the best for your preparations. Bye bye. I will say the recording of the class to you. Bye.